Hello, today we want to talk about the problem real men don't eat quiche. You will find that problem in many textbooks. And we talk about that problem in the context of perfect Bayesian Nash equilibrium. We're going to talk about the problem first and then about the solution. In the solution, we talk about the strategies, the pure Nash equilibria, the mixed strategies, the behavioral strategy profile, and the Bayes rule. One disclaimer for this video is that I would like not dig too deep into mathematical equations and notations. Rather, I would like to provide a good overview about the problem and a better understanding that you know first what to do and how to solve it. Afterwards, you can write down the mathematical equations that you follow in your lecture or the current textbooks you are reading. So the problem is as follows. Tom sits in a pub in Dublin and having a great time. A stranger walks in and is looking for trouble. The stranger wants to bully Tom, but only if Tom is weak. If Tom is tough, the stranger does not want to bully Tom. However, the stranger does not know whether Tom is tough or weak. He only knows that Tom is tough with probability 4/5 and weak with probability 1/5. If the stranger decides to bully, Tom will move if he is weak. However, he will fight back if he is tough. Tom receives 2 points if the stranger differs. The stranger gets 1 point for his correct guess. In addition, Tom gets an extra point for not choosing something he does not like. Tom can signal to the stranger if he is tough or weak. If Tom drinks beer, he signals that he is tough, is a tough guy. If he eats quiche, he signals that he is weak. So let's start with the solution. First, determine the strategy for both players, derive the extensive form of the game, and find all pure Nash equilibria. I have not written down any questions to it because every tutor or lecturer or professor asks different questions about the problem, but most of them, they are all the same, and you have to start with defining the strategies, transfer it into an extensive form, and find all pure Nash equilibria anyway. So we start with that. The strategies are given for player 1, which is Tom, is QQ, QB, BQ, and BB, where Q stands for quiche and B stands for B. For player 2, the stranger, are the strategies AA, AD, DA, and DD. A stands here for attack, and for example, QQ means the first letter is the action when Tom is tough, and the second letter is the action when Tom is weak. Just a reminder for that. And now we're going to derive the problem into the extensive form, and that looks like this. What might be new is for you that nature comes into game, which is and nature decides whether Tom is tough with the probability 4/5 or is weak with the probability 1/5. Further, when we talk about perfect Bayesian Nash equilibrium, it consists of 2 components, which is we have incomplete information, that's why you can see here the dashed line, and it's sequential or dynamic, right? So the stranger does not know whether Tom is tough or weak. In detail, he does not know if we are here on the left-hand side or here on the right-hand side. He only knows the probabilities. And the payout are derived from the text, and we go through it from left to right. So we are here on the left-hand side where Tom is tough and he eats quiche and the stranger attacks. Then both get 0 because the stranger did not make a correct guess and Tom is tough, so he fights back. On the next path, the stranger differs, meaning he gets 1 point for the correct guess, and Tom gets 2 points. Actually, you can see the 2 points as initial endowment, gets 2, but not an extra point because he eats quiche even though he is a tough guy, right? And now we are here on this side where Tom drinks beer and the stranger attacks while Tom is tough and he fights back. So he has the outcome of 1 and the stranger gets 0. And here the stranger differs, which makes him a correct guess. That's why he gets 1. And Tom for drinking beer while he is tough, meaning he does drink what he likes and does not eat quiche. So that's why he has 3 points. And that's all for the left-hand side. Now on the right-hand side, where nature decides that Tom is weak, eats quiche, and the stranger attacks. That meaning he makes a correct guess and that he gets 1, and Tom receives 1, meaning from his initial endowment, which is 3, he loses 2, right? Because he ate quiche, gives him a surplus from 1 and then loses 2 is 1. And the stranger here differs from or does not attack, then he did not make a correct guess, and Tom gets 3 points, outcome, payoff, whatever you like. And further, then Tom drinks beer, even though he's weak. The stranger attacks, makes a correct guess. Then Tom has 0. And yeah, stranger gets 1 for the correct guess. And the stranger differs here on the last path, meaning that Tom has 2 because he drinks beer even though he's weak, preferred quiche, and 0 for the stranger. Yeah, that's when you see it for the first time, it's not so easy to understand. Maybe you have to go through it one more time. And now I think what you brought to watch this video is what you brought you here for watching this video is how to derive the matrices from the extensive form, right? So first, what you do is you split the extensive form, meaning the decision tree, into 2 parts, meaning for the tough side and for the weak side. We start with the left-hand side where Tom is tough because that's what nature decides. And you set up the matrix with player 2 on top and player 1 on the left-hand side. So meaning player 1, Tom, looks from left to right and player 2 from top to down, right? And all these strategies that we defined earlier. So how do we start? One trick is here, and I'm going to explain it like you may explain it to your colleagues in simple phrases that it's better to understand. One trick I like to say is, if you're on the left-hand side, meaning Q is the action if Tom is tough, so meaning the first letter, then you have to check also for the first letter on player 2, meaning QA. So you have to follow the path from Tom here. It starts here, Q and then A. So QA. In more detail, for this matrix, you only look on the first letters of these strategies from player 1, meaning from Tom. The second does not really matter for this case. So you check for QA is 0, 0. Then you check for QA again, still 0, 0. QD, then QD to 1, and also QD. Then it repeats for the next row, right? And then it changes here. Then you have the B, meaning this, let's say the second option for Tom, But that means, on the other hand, you also have to check for the second letter for player 2, right? Because B is the second option, then you check for the second letter. Then you are here on B, and then attack BA. Then BD, 3-1. Then again BA and BD, right? And that repeats also for the last row. That's the left-hand side. Again, check only for the first letters in the 4 strategies from player 1, and then find the corresponding letter for the first letter of Tom, right? So, but don't forget the probability of being tough, meaning that if you find the table for the left-hand side, you have to multiply each cell, let's say each value in each cell by 4/5. That gives you the final table for the left-hand side. I did not write it in fractions because then might be easier to see directly what's bigger or less. And if you did that, you have to do it also for the right-hand side. And you proceed in the same way as in above, meaning you set up the matrix, and then the next trick, or let's say it's a similar trick, but for the right-hand side, you only check by player 1 the second letter, because we're on the right-hand side, meaning Q is the action taken when nature decides Tom is weak. Yeah, and then meaning you check for the corresponding letter for player 2, and that is the first letter. Then you have QA 1-1, QA 1-1, and now QD 3-0, and QD also 3-0. Then it changes to the letter B, and then you have to check for the other letter on player 2 strategies, meaning you have BA, which is BA 1-0, then BD 2-0, BA 1-0, and BD 2-0, right? And then it repeats for the third and for the fourth row. So the first and the third row are the same, and the second and the fourth are the same. In this case, I would not put my hand into fire if it's for each task that is similar, but for this case it's the same. And yeah, then you multiply the whole matrix with 1/5. Yeah, and then you have the final table for the right hand side, and then what you have to do next is to add together table 1.3, which is the final table for the left hand side, with table 1.4, which is the table for the right hand side, and you add it up in a way that each corresponding cell is added with each other, right? So you have 0 plus 0.2, 0 plus 0.2 gives you this new cell, and so on, right? We can do it here for, let's go for this one, QBDA, which is 1.6 plus 0, and 0.8 plus 0.2 is 1. And if you go through it, you get your compiled, I call it now compiled final table, and in this compiled final table you can find your Nash equilibrium, or let's say Nash equilibria. And we will see that there are two of them, namely BBAD and QQDA. Now, depending on your motivation or your current studies or level or whatever, that's pretty much it if you want to stop now. But you can also go deeper into that problem, because now you see that player 1 actually wants to play only BB, because 2.8 is slightly larger than 2.2, right? And player 2 can mixes between AD and DA, because the payoff is the same. And if he does so, player 1 has the incentive to switch to BQ, right? Because here on DD, BQ, DD, he gets 3 points. So the outcome of 3. And now, as I said, if player 2 wants to mix, then that's the buzzword for mixed strategies, right? So we have to find a value for P in which player 1 does not want to switch, and also a value that he wants to switch. We do that by solving for the mixed strategy, but let's see here first. Tom plays BB and Strange AD, so that's the first Nash Equilibrium. Tom plays QQ and Strange ADA. However, Tom will play BB since the possible outcome is larger compared to QQ, and Stranger will mixes between AD and DA, meaning that Tom has the incentive to deviate to BQ. All right. And the question is, for which value of P does Tom deviate to BQ? Yeah. So you set up the mixed strategies, the mixed Nash equilibrium, and you find, I guess if you are watching this video and you are on the chapter Perfect Bayesian Nash equilibrium, you know how to do that, right? So here's the equation that you can check if you understand it. It comes from this compiled table, and then you set it up and solve for P, and P is larger than 0.5, and that means if P is less than 0.5, Tom deviates to strategy BQ. And the Nash equilibrium BB AD, where he does not deviate, is a Nash equilibrium if and only if, there is an F missing, if P is the element of 0.5 and 1, meaning it has to be 0.5 between 1 and 0.5. And that might be a further question on your exam or on your homework. And further, what is also a nice question is to find the behavioral strategy profile. Let's imagine you have mixed strategies given, which in this case are not Nash equilibrium strategies, where you have 1/8 QQ plus 1/4 QB plus 1/8 BQ plus 1/2 BB for Tom, and also a strategy for the stranger, right? And here again, the first letter of Tom is the action if he is tough, and the second letter is the action if he is weak. For each player, we have 4 different outcomes that are given here, so it's conditional probability. Here we have the probability of beer given tough, and that consists of 2 probabilities, namely probability BB plus probability BQ, and that is 1/8 plus 1/2, and that equals 1/5/8, the fraction of 5/8. And how do we get to that solution? First, the first letter is the action taken if he's tough. So, and here we have given that Tom is tough and drinks beer, meaning we check on his strategy only the numbers or the fractions where b is the first letter. And we see that here, BB, 1/2 and 1/8, right? That's pretty much it. And you go through that also for Quiche, given that he is tough, and then you check where Q is the first letter, and then you see it here, QQ and QB, write it down, then you have 3/8. And then similar to B, given that he is weak, and then, but then it changes, then you have to check where B is the second letter, namely BB and QB, yeah, that's correct. And then you get the outcome of 3/4, and then similar to Q, given that he is weak, a Quiche that he is weak, given that he's weak, and then you have QQ and BQ, and that's 1/4. And you do the same for the stranger, and then you get the outcomes, or let's say the probabilities. Yeah, that's probabilities. And why do we do that? Because there's might be a further question on that. I really highly interesting questions, and popular among teachers, because we talk about perfect Bayesian Nash equilibrium, and obviously it's in line with the Bayes rule, right? And then you may be asked to solve the Bayes rule or find a certain probability that you can find with the Bayes rule. Namely, what is the probability that Tom is tough if he drinks beer? Is the probability that he is tough if he drinks beer bigger than Tom being tough if he eats quiche? And you solve that with the Bayes rule. And the first probability is that he's tough given that he drinks beer. And I think if you read in any textbooks or in your slides from university, you find really quick the Bayes rule. And the Bayes rule is something that's not so easy to understand at first, because conditional probabilities with the notations, it's really tough if you see it for the first time, but you can go through it. On the upper part of the fraction in the denominator, you have the probability that Tom drinks beer given that he's tough, multiplied by that he's actually tough. And the last part, that he's tough, that's the probability that determines, that comes from the nature, right? And then you have the same equation here also in the denominator, plus the probability that he drinks beer given that he's weak, multiplied by being weak. And then you can insert the probabilities that we just calculated above in the slides and find the probability that tough given that he drinks beer. And you do the same for tough given that he eats quiche. And then you can find the answer to your question. So that's pretty much it. I hope you did enjoy this video and have now maybe a little bit better understanding. I think you have to go through it one more time, or take your time as much as you want. And don't forget to check the description box, and there's a link where you can download the PDF from my Google Drive folder. And I hope you did enjoy. If you have any questions, leave them below, and you can subscribe and like the video if you like to. Thank you very much.